Last day of January. Well, I'll start by asking, are there any specific things or questions any of you would like me to go over? Finding local max and local min?
Yeah.
So just said local?
Oh, no, especially the maximum.
So are we talking about finding, sorry, one second. Global maximum and minimum or local?
Local.
Okay.
Yeah.
And I would say we don't really specify to start off with maxima or minima or settle points. We just kind of say we're going to do this because we don't really know what we're going to get until we do the process. So sure, let's see. Yes, I have some examples here. Just one second. Sorry, one sec. Yeah. Might be that one. And to be clear, well, did he say whether or not absolute maxes and mins on the closed domain are going to be on the exam? They're not going to be on there? Okay. All right. So sure. Let me see here. Let's look at something like. Sorry, I thought it was hard to just come up with examples here. One second. Thought I had one, then I realized we'd already done that one. Let's do this. One moment, please. Oh, sorry, that's not what I need to do. Sure. Sorry, my brain is like, yes, I know where I'm going. Okay. Let's look over here. I thought I had something all queued up and it's disappeared on me. But there we go. I see. Sure. I'm hiding things from myself. The reminder, definitely make sure you check out the practice exam that I wrote and posted. All right, well, we'll start with this example. It might not be the best ever, but sure. So we're going to find and classify the extrema of, actually, let's look here instead. Sorry, I keep going back and forth here. Sure, let's look at this one. f of xy equal to x squared plus 8xy plus 10y squared minus 4y plus 6. So what's the first step? Find the partial derivatives. So we're going to have fx, which is going to be 2x plus 8y, and then fy, which is going to be 8x plus 20y minus 4. And we're going to do what with both of those partial derivatives? What do I do now? I set them equal to? Right. I'll point out, and this is something that you should recognize, both of these are equations of lines. Right, 2x plus 8y equal to 0 is the equation of a line. 8x plus 20y minus 4 equal to 0 is the equation of a line. So in this particular instance, you're just trying to find the one point where the lines intersect. There's a couple ways to do this. I would probably, in this case, I'd probably solve for one of them instead of equal to. So I'd probably solve for x here and say 2x equals negative 8y. So x is equal to negative 4y. And then take that and plug it into the other equation. So I plug that in for x over here. I'm going to get 8 times negative 4y plus 20y minus 4 equal to 0. So I have negative 32y plus 20y equal to positive 4. Negative 12y equals 4. So y is going to equal 4 divided by negative 12, which is negative 1/3. And then plugging that back in over here, that means x is going to equal negative 4 times negative 1/3, which is positive 4/3. So our only critical point for this problem is 4/3 comma negative 1/3. So now the question, is it a maximum, minimum, or a saddle point? Well, to answer that question, we're going to find our capital D. So capital D equal to fxx times fyy minus fxy squared. In this problem, our fxx is just going to be 2. Our fyy is just going to be 20. And our fxy is going to be 8. This problem is kind of uninteresting in that there isn't anywhere to plug in our critical point, right? We just get this value. That happens more often if your function only has one critical point. If you have multiple critical points, you're often going to have a d where you have an x or a y to plug into. So in this case, we end up getting 40 minus 64, which is negative, meaning we have a saddle. So 4/3 comma negative 1/3 is a saddle. So somebody else asked if we could find optimization problems for local maximum. So I would say actually, usually when you're talking about an optimization problem, it's really more of an absolute max or min. Like you really just set, like the problem is more phrased as find the thing that maximizes this quantity or find the thing that minimizes this quantity, and we're not really using that language, right? Like we just kind of ignore it and be like, yeah, whatever we get, it's going to be the thing we want for the most part. Let's look at kind of a what's what I'm looking for here. A somewhat contrived example. So sure. We want to find two numbers such that the sum of the squares of the two numbers is 18, and we wish to maximize the sum of the original numbers. Again, a bit contrived and a lot of words. So they're giving us a couple things we want to do here, but we really have to kind of interpret what's being said. So we want to maximize the sum of the original numbers. So we're trying to maximize, I would say x plus y, right? If we're just trying to maximize the sum of two numbers, we're trying to maximize x plus y. This problem, I don't know if I like this problem so much, but oh well. Yeah. I realize that. I realize this problem isn't really kind of. You'll see what I mean in a second here. We might cut this problem short because it's not excellent, but so we're trying to maximize f of x y equal to x plus y, and we're given a constraint. Our constraint is that the sum of the squares of the two numbers is 18. So we're told that x squared plus y squared is equal to 18. And this isn't great for us because what's happening here really is if we solve for one of these equations and plug it in the other one, we're actually going to have a function of one variable that we're trying to maximize. So it's not particularly interesting to us. And it is kind of actually gross. Like if I actually try to solve this for x or y, I'm going to get y squared equal to 18 minus x squared. Y is equal to the square root of 18 minus x squared. And if I plug that back in here and then try to take the derivative instead of 0, it's doable, but it's not particularly nice. So sorry, I'm searching for problems here, and I thought I came better prepared than they seem to be here. So let's take a quick look over here. I grabbed a bunch of things and then they all seem to be, yeah, I don't love you either. One second. Yeah. We can look at that one, sure. So let's go back a step and do another one where we find just the critical points and classify. In fact, it might be a good time for you all to try. So I want you to start by finding the critical points, and there might be more than one, of the following function. F of x comma y equal to 12x squared plus y cubed minus 12xy. So work on finding those critical points for a couple minutes, and I'll see if I can find a better question for Julie over here. Let's take a look and see what we get for our critical points here. Taking the partial derivatives, I'm getting 24x minus 12y equal to 0. And with respect to y, we're getting 3y squared minus 12x equal to 0. Certainly, I'm going to look at the least complicated one and try to deal with it. Here, I can solve for y and say 24x equals positive 12y. So 2x is equal to y. Plug that back in for y over here. Then we have 3 times 2x squared minus 12x equal to 0. That's 3 times 4, so 12x squared minus 12x equal to 0. We can factor out a 12x. We're left with either x equal to 0 or x equal to 1. If x is 0, y is going to be 0. And if x is 1, y is going to be 2. So those are our two critical points here. 0, 0, and 1, comma 2. And then we do the, right, so, I mean, it might feel like it's getting a little bit old, but like it's the same thing every time for these, we're finding maximum, min, and saddle points. You find the critical points, and then you find capital D, which might be a little more interesting for this problem. Capital D is equal to, come on in. Let's see, fxx, which is 24, times fyy, which is 6y, minus fxy squared, which is going to be negative 12 squared. Okay, so if we plug in the 0, 0, d of 0, 0 is going to be 0 minus 144, which is certainly negative, so we have a saddle. And then if we plug in 1, comma 2, we're going to get 24 times 6 times 2 minus 144. I don't know what that is exactly, but it's 24 times 12, which is certainly bigger than 12 times 12. So this is definitely going to be positive. And looking at each of our second partials here, whether you're looking at fxx or fyy, either one of those is positive. So our d being positive means we have a maximum or a minimum. And then we know that since our second derivative is positive here, we are concave up, which means we have a minimum. I can't stress enough how nice I think it is to think of it that way, right? If you think about it being concave whichever way, you're pretty confident you'll get the right max or min. So we have a minimum at 1, comma 2. Cool. All right. That's a good question. So we'll do a couple optimization problems here. So I'll point the reason I don't like optimization problems so much is because so many of them just feel very obvious to me. I think it's just my bias. So here's a question we'll do. Find 3 positive numbers whose sum is 12 and whose squares are as small as, and whose sum of squares, I believe. And the sum of, and whose sum of squares, apologies, is as small as possible. And to me, it feels really, really obvious that the answer is that the numbers are 4, 4, and 4. Because you kind of have a symmetry here. If you're looking for 3 numbers that all add up to 12, and there's no reason they have to be different than each other, then it's very likely the answer is going to be that they're all the same. That doesn't mean we can just say the answer is 4, 4, 4, right? We still have to show the work. So here's the work. We want to find 3 positive numbers whose sum is 12. That's our constraint. Our constraint is our 3 numbers. Let's call them x, y, and z. Is that x plus y plus z has to equal 12. We're trying to minimize what? We're trying to minimize the sum of the squares of the numbers. So x squared plus y squared plus z squared. So these people are like, I'm just, well, no, I'm going to say this is the sum of the squares. You don't really even need that though. And I'll point out that in both these equations, if you interchange x or y or z with each other, the equation wouldn't look any different, which is generally a big clue that your answer is going to be to all the things. It's very, very likely that you're the 444 is our answer. But let's do it. So same sort of deal we did before. If you're trying to solve an optimization problem like this, you take your constraint, you isolate one of the variables, usually z, unless there's a good reason to pick a different one, and plug that in for z in the other equation. So here you're going to have z equal to 12 minus x minus y, and we're going to sub that in for z right there. So now our sum of squares, which I'm going to write as a function of just x and y, is going to be x squared plus y squared plus 12 minus x minus y squared. It is not to your advantage to multiply that out. It is definitely preferable to just leave it as is, so that when you take the partial derivative, well, just to not really just not to do the work, right? It's not gonna make your partial derivative easier or harder, but it's definitely more work to multiply that out. So then we take our partial derivatives like we've done every time. We get 2x plus 0 plus the derivative of this thing squared is going to be 2 times 12 minus x minus y to the first times -1. And then for fy, same deal, 2y plus 2 times 12 minus x minus y times -1. Set both of those equal to 0 and solve. Now, no, not really. Again, this is kind of the situation. We have essentially the equations of two lines, and we're going to try to deal with them. Let's see what we get here if we simplify this a bit. So simplifying this, I have 2x. Don't forget the -1 here. You know what would have been smarter to do? Well, it's too late now. Is to say this is a -2 times all that. So I have 2x minus 24 plus 2x plus 2y equal to 0. And I have the same thing down here, essentially. 2y minus 24 plus 2x plus 2y equal to 0. And this is never fun at this point. You could either isolate one variable and plug it in for the other one, or you could try to do the thing where you eliminate variables. I feel like eliminating usually makes me think too hard. I feel like it's easier mentally just to solve for something here. So I'm going to solve for y here. So divide everything by 2 and bring everything else to the other side. So I'm going to have 2y equal to positive 24 minus 4x. So y is equal to 12 minus 2x. I'm going to plug that in for the y's in this equation. And I guess I should simplify this equation first. So I have 4y plus 2x minus 24 equals 0. And I'm going to plug that in for y right there. So I'm going to have 4 times 12 minus 2x plus 2x minus 24 equals 0. Ugh. 48 minus 8x plus 2x minus 24 equals 0. 48 minus 24 is 24. -8 plus 2 is -6x. And surprise, surprise, we get x equal to 4. And then we plug that back in over here. If x is 4, y is going to be 12 minus 2 times 4, which is 12 minus 8, which is also 4. I don't think for optimization problems that you need to spend the time to show that it's a maximum or a minimum. But if we wanted to, we could. Right? We could totally find capital D. D is equal to fxx, which is going to be kind of gross. So this is actually a good point here. This is where looking at this is not the best. I'm looking at my fx over here where I multiplied it out, and then fxx is going to be 2 plus 2, which is 4. Fyy is going to be 2 plus 2, which is 4. And fxy is going to be 2. And look here, you have no choices. Your d is positive, and your second derivatives are positive, which means you're concave up, which means you have a minimum. So we must have a minimum. So x equals 4, y equals 4, and z equals 12 minus 4 minus 4, which is 4, is are the numbers whose sum is 12 and whose sum of squares is minimized. Another way I could have asked this question, it would have been to say, what is the minimum sum of squares of three numbers that add to 12? And then the difference is, instead of telling you what the numbers are, 4, 4, and 4, you'd say, oh, the minimum sum of squares is 4 squared plus 4 squared plus 4 squared, which is 48. Well, let's look at another one that is slightly more interesting. Okay, yeah, that's a good one. Yeah, sure, that's kind of funky. So, yeah, I could almost see your instructor asking a question like this. Find the point or points plural on the surface y squared equal to 9 plus xz that are closest to the origin. Okay, whenever you have these physical things in space being close to some other thing in space, you always have to reinterpret the meaning of that question. What are they asking us to really do? They're asking us to minimize the distance between any point on the surface and the origin. So we have some surface. I don't really actually know at all what it looks like. But let's pretend, we've got some surface. It looks like this. I don't know, weird like that. And there's some point on it right there, X, Y, Z, that's going to be the closest to the origin. What we're really trying to do here is find the point X, Y, Z that minimizes the distance D. So we want to minimize D, which is equal to the square root of X minus 0 squared plus Y minus 0 squared plus Z minus 0 squared. Now, hopefully you all remember something important I said about minimizing distance. Instead of minimizing the distance between two things, we can do an easier thing and minimize what? Right. You can either say what's underneath the square root or the square of the distance. So instead, minimize the distance squared. And let's go ahead and simplify this as well, right? X minus 0 is X, Y minus 0 is Y, and Z minus 0 is Z. So this is really just X squared plus Y squared plus Z squared. As is often the case with these kind of problems, it's going to start off as being a function of 3 variables and we need to be a function of 2 variables. So we need to have some constraint. But our constraint in this kind of situation is already given to us, right? We don't have to search for it. Our constraint is that our point has to be on the surface. So it has to be true that y squared is equal to 9 plus xz. And this is a prime example of not making your life hard on yourself. You don't want to solve for z here, right? I know we usually like to isolate z, but here you've already got y squared all by itself. So we're really just going to take y squared and replace it with 9 plus. We're not even going to square root both sides. We're just going to say, hey, cool, d squared, which now we're going to say is our function of y and z, not y and z, James, x and z, apologies, is going to be x squared plus y squared, which is 9 plus xz plus z squared. Cool. Now our distance squared is a function of just 2 variables, and we know how to deal with a function of just 2 variables. We're trying to find the max or min or saddle point. In this case, the minimum. So take the partial derivatives. Fx is going to be 2x plus 1 times z. And similarly, fz is going to be 1 times x plus 2z. I couldn't help myself without, can I help myself? Maybe, I don't know. I could probably help myself, but I'm not going to help myself from pointing out the symmetry here, right? These equations essentially look like each other if you switch x and z. So we're probably going to get critical points that look like either 0, 0 or 1, 1 or 3, 3 or something where the x and the z match each other. So here, we're going to say z equals negative 2x. We're going to plug that in over here. So we're gonna have x plus 2 times negative 2x equal to 0. X minus 4x equals 0. Negative 3x equals 0. So x equals 0. And you plug that back in here, you get z equal to 0 as well. You might have been able to recognize that 0, 0 was going to be the point of criticalness, the critical point, because again, these are just equations of lines, and these two lines intersect at the origin. They both go through the origin. They're not the same line, so they have to, that's gonna be the only point of intersection. So then, do we check to see if it's a minimum? Sure. Again, kind of boring here. Our capital D is equal to fxx, which is 2, times fzz, which is also 2, minus fxz, which is 1 squared. And just like before, this thing is always positive and always has a second derivative that's positive. So positive means the max or min. Our fxx being positive means we have concave upness. So it has to be a minimum. Usually you do not need to check when you're doing an optimization problem, if it's a max or min. I'm not done though, because the problem said find the point or points on the surface y squared equal to 9 plus xz. So I got x equal to 0, I got z equal to 0, but I still have to find the corresponding y value. Well, that means y squared is equal to what? 9 plus 0. So y is going to be what? Yeah, so there actually are 2 points. Y is plus or minus 3. So my 2 points are 0, comma 3, comma 0, and 0, comma negative 3, comma 0. Kind of interesting. Cool. What else? So there are other things, right? We didn't, I know like optimization and maxes and mins are like the most recent thing, but there were other things we did earlier on in the quarter, like finding directional derivatives, right? We can do, let's do a directional derivative. Let's see if I can find that. Yeah. I don't know. Let's see. So let's say we have the following function. Things in order here. Go back for a second. 1 second. Yeah, there we go. Oh, yeah, someone else just said unit vector direction. Cool. So let's say we have the function f of x comma y equal to 2xy plus x minus y cubed. And we want to find the derivative at the point 1 comma 2 in direction. I should ask real quickly, did he ever talk about the difference between, I know I talked about it in class, but did he ever talk about the difference between finding the direction, the derivative in the direction of a vector versus in the direction of a point? Probably not. So he probably won't ask about that, but just remember, like if you're pointing towards a point, it means you have to find the vector between the 2 points before you start doing the directional derivative thing. But he's probably not going to ask that, so let's just be normal about it. So if in the direction of the vector v equal to 2 comma 7. Or he might write it as 2i plus 7j. It's another way of writing a vector. Okay, so usual process. We find our gradient, which is just the vector of partial derivatives. So the gradient of f is going to be the partial with respect to x, comma the partial with respect to y, which in this case is going to be 2 times 1. Sorry, 2 times y, apologies, plus 1, excuse me, comma, fy is going to be 2x minus 3y squared. So that's our general gradient, and then we're going to find the gradient at the point. So we're going to plug in 1 comma 2 and get the vector 2 times 2 plus 1, comma 2 times 1 minus 3 times 2 squared, which is going to be 5 comma 2 minus 12 is negative 10. So there's your gradient vector. And then we're going to dot that with the unit vector in the direction that was given. So our directional derivative is going to equal this gradient vector dotted with our vector v, but unitized or normalized. So the vector v divided by its own magnitude. I like to put that out in front, so I'm going to say we have 1 divided by the magnitude of v, which is the square root of 2 squared plus 7 squared, multiplied by the gradient of f, which is 5 negative 10, dotted with v, which is 2 comma 7. So that's going to be 1 over the square root of 4 plus 49, which is 53, times, let's see, 5 times 2, plus negative 10 times 7. So it looks like we're looking at something like negative 60 divided by the square root of 53. That means we're decreasing, right? If we move in this direction from this point, we are going down the hill, not up the hill. Bonus question. In what direction is this function increasing most rapidly? Never feels like a bonus. In what direction is the function above f of xy equal to 2xy plus x minus y cubed? In what direction is f of xy increasing most rapidly? From the point 1 comma 2. Now, you can't ask about what direction you're increasing most rapidly if you're not saying at what point you're starting at. Okay. So there's a very, 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 very straightforward answer to this question. Whenever you're asking about what direction are we getting biggest, fastest, the answer is always the direction of the gradient. So whatever the gradient is, that direction is the direction that is our answer. So you can answer this one. I think there's 2 valid ways to answer this, and it kind of depends on what your teacher wants. You could either say the direction is the gradient of f, which is 5 comma negative 10. Or you could normalize this and say it's gradient of f divided by the magnitude of the gradient of f, which is 5 comma negative 10 divided by the square root of 25 plus 100. But I don't think he's talked about wanting your direction answers to be unit vectors necessarily, so you could probably be good either way. Someone says, oh yeah. Someone said, I think the quiz had 2 problems that showed both cases of directional derivative problems. All right. And then bonus question. How steep is the slope in the direction of maximal increase? Second bonus. It's like second breakfast. What is the slope in that direction? Again, the answer is always the same type of thing. The direction is the direction of the gradient vector, and the steepness or the slope is the magnitude of that gradient vector. So in this case, the answer is the magnitude of the gradient of f, which is going to be the magnitude of the vector 5 comma negative 10, which we already found, which was the square root of 125. I would be shocked if you didn't have a question like this on your exam somewhere, asking in what direction was the maximal increase or maximal decrease and what that value was. So let me ask you quickly, if I asked you instead, in what direction were we having the maximal decrease or the most rapid decrease, what would I do? I would take my vector that was in the direction of the maximal increase and turn around. Everything becomes the negative of what it was. So I'll just write it down here. The direction of most rapid decrease is going to be the negative of your gradient vector, which is going to be negative times 5, negative 10, which is the vector negative 5, comma, positive 10. I've seen this question phrased before as like, what direction do we need to travel in so that we ski down the hill as fast as possible is often been the way I've heard it phrased. Okay, what else? What else is on our minds here? Oh yeah, sure, okay. Let's do one more. Yeah, we have a little time. Monday we'll talk about that double integrals, but that's Monday. Sure. So yeah, I like this question. So given the equation e to the z plus x squared z minus y z squared plus x to the third equal to 17 plus y. Find sure del z del y. And the intention here is to not do it using to not do it using the implicit differentiation, right? Like we don't want to just say z is a function of y and then differentiate both sides with respect to y and so on and so forth. The idea here is to use the fact that this is going to equal negative fy over fz, where we take this equation, set it equal to 0, and the thing on the left is going to be our f. So we have to do a little bit of work first. We have to say, cool, rewrite this as e to the z plus x squared z minus yz squared plus x cubed minus y minus 17 equal to 0. And this is your f of x comma y comma z. So really this question is just about, do you remember this weird formula that's in the book? To be honest, like, but it's easy to remember if you remember, like, it's always just whatever your partial derivative is, it's those, yeah, whatever your derivatives or partial derivatives, it's just the partial derivatives of your function f flipped over in the opposite order. So y is on top, z is on the bottom. We ignore x in this case. So that's going to be del z del y equal to negative fraction. So on top, we're going to have the partial with respect to y. So 0 plus 0 minus 1 times z squared plus 0 minus 1. They made that look terrible by putting all those x's in there. And then fz is going to be derivative e to the z is e to the z. Derivative x squared z is going to be x squared. Derivative yz squared is going to be 2yz minus 2yz. And that's it as far as the z's go. And I don't think you need to distribute the minus sign to get to the top or the bottom, but if you really wanted to, you could distribute it to the top and say you have positive z squared plus 1 all divided by e to the z plus x squared minus 2yz. But I really, really, really don't think you should do that. Yeah. So like this part here, so del z del y really is, so if this is my f of x comma y comma z, the top part here really is just the partial derivative of this with respect to y on top. So yeah, you could think of it, instead of saying fy, you could also think of it as, this top part is del f del y. And this bottom part is, I think that's what you said, I just didn't hear it, is del f. All right. And everyone's super enthused on a Friday afternoon when it's rainy out and there's 5 more minutes left. I don't think we need any more problems, but so what should we think? Okay, so you guys have taken math here for a couple of quarters now, right? Or at least for 1 quarter, right? You took 17B last quarter. I don't know when you took 17A or if you took somewhere else. But you kind of know, right? You know how to take tests, right? Use your smart test taking skills. Don't get stuck on something. If you get stuck, move on to the next thing and come back later. I really wouldn't simplify anything until I was done with everything else. Mostly because also it's easy to make mistakes simplifying. So definitely like be smart when you're taking this test. What time's your test on Monday? Like what day? What time is your class on Monday? I know it's the same time every day, but like, yeah. So, right, make sure you do, if you have class before, you skip it or not, depending on what you want to do, right? Get a good night's sleep, eat some breakfast, do the usual things so that you are prepared like you normally would be. Just like, so just for example, like tomorrow, I'm going to be doing a rowing race and I'm going to make sure that in the morning, like I eat breakfast like I usually do, so that and like I warm up well. So like you have to prepare, practice how you're going to play, right? Prepare, practice how you're going to play on Monday. Do all the smart things. Don't do something stupid on Sunday night, right? Like be smart. And right, the weather's going to be terrible. It's not like you want to do anything fun this weekend anyway. So study over the weekend. Don't study too much, but make sure your brain's ready to go, and you guys will be fine. It won't be that bad. He writes pretty reasonable tests mostly, but I will also remind you that the practice exam I wrote is not exactly verbatim the exam he gave whenever he gave it, but it's pretty close to it. So that said, it doesn't have any optimization problems on it, so you should also practice some of those, but practice a little, not too much, and you'll be fine. I have office hours as usual, and I'll see you all on Monday where we will talk about double integrals, not double derivatives. You're welcome, and I hope it goes well. I imagine it will.